everyone. This is Sachin Fiske from Electrical Engineering Department, S&D College of Engineering and Research Center. Today we are going to start the Z transform. Here is the introduction related to Z transform. The Z transform is a sequence of x of n is x of z is equals to summation of n tends to minus infinity to infinity x of n into z to the power minus n. The Z transform can also be taught of an example of x of z that the transform a sequence of the function x z of x of n is equals to summation of n tends to infinity to the infinity x of n into z to the power minus n is equals to x of z. In both the cases, it is a continuous complex variable. We may obtain the Fourier transform from the Z transform by facing them as a substitution of e to the power j omega. This corresponds to the restriction and also with z is equals to r into e to the power j omega. So x of r into e to the power j omega is equals to summation of n to the power n tends to minus infinity to plus infinity x of n into r to the power minus n into e to the power minus j omega n. That is, the Z transform is the Fourier transform of the sequences, and for r is equal to 1, this becomes the Fourier transform of the Fourier transform. Therefore, the corresponds to the Z transform evaluation. The inherently periodically the frequency of the Fourier transform that is the Z transform is the sequence, and for r is equal to 1, this becomes the Fourier transform of x of n. Inherent periodically frequency of the Fourier transform is captured naturally under this interaction. The Fourier transform does not cover for the all sequences, and the infinite sum may not always be finite. And similarly, the Z transform does not converge for all the sequences or for all the values of Z. The set of value of Z for which the Z transform converges is called as the region of convergency. And the Fourier transform of x of n exists in the sum of summation of minus infinity to plus infinity n tends to infinity where x of n is convergence. However, the Z transform of x of n is just the Fourier transform of the sequence x of n into r to the power n. Having the series convergence to x of z is equals to 1 upon 1 minus a to the power z minus 1 is equal to z upon z minus a. Since it is just a geometric series, the Z transform of the convergence for any finite value of is shown in Z plane. The Fourier transform of only exists if the ROC includes the unit circle, which requires that t is less than 1. On the other hand, if Z is greater than 1, then the ROC does not include the unit circle. And the Fourier transform of the system. This is consistent with the fact that these values of the sequences u of n is exponentially growing, and sum therefore does not converge. For example, left side exponential sequences. Now consider the sequence a to the power minus a to the power n into u of minus n minus 1. This sequence is a left-sided because it is non-zero only for less minus 1, and Z transform is x of z is equals to minus summation of n is equals to 1 to infinity a to the power minus n into z to the power n is equals to 1 minus summation of n equals to 0 to infinity a to the power minus 1 into z to the power n. Note that the expression for the Z transform and the exactly the same as for The right-handed exponential sequential region of the convergence is different, specifying the ROC is therefore critical while dealing with the Z transform. Second example is the sum of the two exponentials. So the exponential of 1 by second n u of n plus minus 1 by 3 to the power n, where u of n is the sum of the two real exponentials. So Z transform is the example for the right-handed exponential transform. In this sum convergence for theta is greater than or equal to 1 by 2 and the second order for greater than 1 by 3. The combined transform Z transform therefore converges in the intersection of these two regions, namely n is greater than or equal to 1 by 2 in this case. So x of z is equals to 2z in brackets z minus 1/12 upon z minus 1 by 2 z plus 1 by 2. The pole zero plot and the region of convergence for the single signal is shown in the figure. Since there are only a finite number of the non-zero terms shown and sum of all the convergences when n to the power minus 1 is finite, there are no restrictions of this value omega, and the ROC is the entire Z plane with the exception of the value given in the system. Note that the numerator polynomials are at the value zk is equals to a into e to the power j 2 pi k upon n, where the value of k is equals to 0, 1, 2, 3 up to n minus 1. Since this value satisfies the equation. Some properties of the region of convergence. The properties of the ROC depends upon the signal, that the signal has a finite amplitude and that the Z transform function. The ROC is a ring or disk in the Z plane centered on the origin, that is the value lies between 0 and infinity. The Fourier transform of convergence absolutely if and only if the ROC of the Z transform includes the unit circle. The ROC cannot contain any pole. If x of n is a finite duration, that is 0 except on finite interval, then the ROC is the entire Z plane except perhaps at x is equals to 0 or z is equals to infinity. If x of n is a right-sided sequence, then the ROC extends overwhelmed from t outermost finite pole to infinity. If x of n is a left-sided, then the ROC extends inward from innermost non-zero poles to is equals to 0. A two-sided sequence, neither left or right-sided, of the ring in the Z plane, bounded on the interior of any exponential, not containing any poles. The ROC is connected region. Formally, the inverse Z transform can perform the Cauchy's internal. However, the discrete Laplace inverse transform system is simple and sufficient. If one is familiar with the common Z-plane, inverse can be found by inspection. For the example, one can inverse them, that is x of z is equals to 1 upon 1 minus 1 by 2 into z to the power minus 1, to mod of z is greater than 1 by 2. Also, if x of z is the sum of the term, then one may be able to do the term by term inversion by inspection, yielding a sum of terms. Thank you.